So I probably would accentuate less on the theory and more on the applications. The implementations, they become clear of what, during the exposition. I have implemented it in several ways. And so you can see here in this, we have a cloud of points, and we want to fit some curves. So you can see here that, say, this green curve is the least squares fit, and the other curves, they come from quantile regression. I'm going to give a more rigorous explanation of what quantile regression is, but basically, if we have a cloud of points, I do want to make a curve which will guarantee, let's say, 95%, looking at this top curve, 95% of the points are below it, and so forth. So I'm going to illustrate this with with a conversational engine. So for example, if I have loaded the temperature of Atlanta, and if I say plot data, we do get some data plotted. On here you see this is the input from the user of the conversational engine. This is what the data is being spoken, and in the bottom panel you see the actual result. And I'm going to magnify this too. And so what is the regression quantiles? First, I'm going to do least squares fit to just illustrate what is going on. And all right, so my least squares fit here. I need to use functions with which I'm doing the fitting, and I'm going to use, say, 1x and sine of x divided by, say, 10 power 6. And you can see this green curve has been fitted. I can do something better, like, for example, find free regression quantiles. Again, sorry. So press too many buttons. But here we see these are the regression quantiles, which they follow the signal much better. And what else I can use regression quantiles is to for example, do a command like compute the top outliers. And the way I have found these outliers is that I'm finding this curve in blue is constructed as such that 98% of the points are below it. So everything above it is considered to be an outlier. So basically in the talk I'm going to explain how come I'm computing this quantiles and some further applications. Correct. So obviously it depends how do you define the outliers. I mean, you can obviously find, say, the median and then look at some interquartile distance. But you see, you can actually do that with this regression quantiles. I can find the I'll show later on. You can actually extract the interquartile distance in such a way where it is actually time dependent. And this is one of the things we're going to kind of see later on. All right, so the theoretical background is there's an observation that similar to least squares, we can make a formulation of the quantile regression which uses a minimization function. We're minimizing, instead of minimizing the 2 norm, the Euclidean norm, we're minimizing the absolute value, which is norm 1, I think, norm 1, norm infinity, whatever. In order to have these curves to be under 95% or 75%, this is how the problem is reformulated. What is interesting here is that in order to solve this problem with linear programming, you need to actually introduce slug variables. You need to reformulate it. So instead of minimizing this function, I'm actually making constraints from this function, and I'm trying to minimize the slug variables, the sum of the slug variables. This is kind of the trick which allows the computation. I'm not going to dwell on this too much because of time purposes, but my implementation uses linear programming, and I have several methods. In linear programming, you can use also, instead of using linear programming, you can also use minimize and minimize. They are most suitable for more symbolic type of computations. Linear programming has several methods. It has an interior point simplex method, also has a library called CLP, which it can be used. So here, you know how Mathematica has a function called findFit. And so this is the first implementation in which we start with some kind of noise. We have figured out that we want to calculate these quantiles here. And I'm just by looking at this data, I see that, for example, we can use this number of functions. Oh, sorry, these concrete functions, like 1 and x and square of x or logarithm of x. So they seem to kind of fit this this type of data. So after I have determined the functions, I have a function called Quantile Regression fit. And in order to do the Quantile Regression fit, I need to generate the data first. So this is corresponds to findFit, and you can see these are the functions found by Quantile Regression. I mean, obviously, I can use the standard least squares corresponding function, and here we can plot them. So these are the functions which we just found, and you can see how they compare with the least squares. We can verify, by simple counting, how well these quantiles, regression quantiles, these curves, how well they separate the data, and we see that we're in pretty close agreement of what we wanted to do. So further, one of the useful things about this is that if your data, for whatever reasons, it has some systematic error, like for example in this particular case, all the values above certain threshold are larger, then we actually can see that the regression quantiles at the bottom, I mean the ones which the 95 one has changed, but the others they have not, and obviously the least squares have changed. So this is one of the examples of how robust quantile regression is. Quantile regression corresponds to finding the median in one-dimensional case, and least squares corresponds to finding the mean. I mean, we can see that here the functions have changed. Have not changed they're basically the same functions from the previous case. I mean, this table just compares the alternative quantiles. I mean, you can basically believe me, the functions found with the non-biased data and with the biased data. And again, I have a table which compares the two, and we can see that the ones with the least squares is actually quite different. It has quite different structure. All right, so I mean, this example can be extended. I mean, I want to have more time to discuss other things. Obviously, instead of using fitting functions, instead of like specifying the basis functions on our own, it is a good idea to find this fitting automatically. And one way to do that is to use a basis of functions in the time or space or x interval. And I can use a variety of functions, I guess, but you can use B-splines, which are implemented in Mathematica. And so after we find the quantiles, the quantile curves. This is what we get as a result. And what is the benefit here? You can see that if I use fit, I need to specify what functions I want to be used in order to be fitted. Here with the quantile regression, with the B-splines quantile regression, this kind of happens for free. The only thing I need to specify is the number of knots I want to use. And if I use a smaller number of knots, this is going to be more chopped. The approximation is going to be less fine. And you can see like how the least squares kind of follows, with the previous result, follows the curve. Obviously, if I do the more detailed my quantile regressions are, the better this is going to fit. Now, as I said, the methods, the Quantile regression package, which you can find actually on GitHub, and there are references in this talk, this presentation. It does take a method option like linear programming, and then you can specify the actual method used by linear programming. You can put simplex or interior point here. You can also use minimize, but you'll get a warning that for large data, minimize is not suitable to be used. You can see a case here, but this is interesting. This means it's overtrained. I mean, obviously, if you put larger number of basis functions, so we have much more basis functions here at the bottom, you kind of overfit the regression quantile, the top one. All right, so I would say this was more or less, this is the implementation. If you want to see more of the theoretical results, there in this paper also, in the bottom slide, the last slide of my presentation, there are lots of links where to find documentation and examples on the web and PDFs. So this is the first, in my opinion, obvious application of quantile regression is to find outliers. And this is an example for outlier definition taken from MathWorld. So you can see Eric Weinstein, who maintains MathWorld. He has taken 1,000 random points, and then he inserted another point. And point number 30 is being 6,000. Now, we want to detect this point. Obviously, if you are just looking at the x values or just looking at the y values, you cannot see this point as an outlier. So you need to have some kind of other method. And so if we do some quantile regression fitting, I did it here, you can see that these points in blue are generated from my quantile regression function, which I calculated at 95, quantile 0.95. And you can see that, yeah, I have clearly detecting the outlier. And this is more or less how this code works here. In this example, this is how the outlier regression goes. I also, of course, we can be interested in the bottom outliers, and yeah, basically this is one of the basic applications. Another interesting application is the estimate of the conditional density of distributions. I have taken this example from Roger Koenker's book, who is a big proponent of quantile regression. He introduced a lot of theory and computations, like actual code methods, how to compute quantile regression really fast. Roger Koenker is a professor of economics in University of Urbana-Champaign, so he's basically really local. And in R, the packages in R and SAS use the code written by him. So, so in this particular example, I have taken the temperature of Atlanta in the last 14 years. And now we can ask ourselves, how big is this? Do you see this? We can ask ourselves, can we predict the temperature of today using yesterday's temperature? So, what is the, in his book, Roger Koenker uses Melbourne. I'm actually afraid that with this internet connection, I cannot download the data. So I'm not going to do it. I'm not going to reevaluate the data. But so, we, in a sense, we have a very simple task. We're trying to, we think that we can predict the temperature, today's temperature, knowing yesterday's temperature. And so this is the analysis that we can do using regression, quantile regression, is to fit a big number of regression quantile curves, like here. Now, at any point, say if I have taken this temperature 10, I can actually reconstruct what is the distribution of the today's temperature, given that yesterday's temperature was 10. So that's why this, I'm saying we're doing estimation of conditional density. So we know what happened in the day before, and we are trying knowing that this was the temperature yesterday, we're trying to figure out what are the statistical properties of the temperatures today. And yeah, with regression quantiles, we can completely reconstruct the cumulative distribution function. I mean, I have shown it here on temperature 15, which is basically here, yeah, this one. And so we can do further some conjectures. We can also calculate the PDF and compare the PDF, the CDF, and do other things. So on this plot here, in a gray solid line, this is the 15. This is at 15, and the other dashed curves. These are the quartiles. Sorry, not the quartiles. These are these quantiles at 0.5, 25, 5, 75, and 95. All right, so we can actually we can observe this in a more systematic way. And again, the solid line, I'm not sure how clear it is, but there's a solid gray line here. And this is at temperature -1, I guess. Yeah, I apologize about this. I should have checked. Maybe it's because of the zooming. But it is at -1, and you can see the green line. This is the median. So if the temperature is around -1, or in this particular case is 0, we would expect the temperature to increase. So in Atlanta, when the temperatures are low, you're most likely to have the temperatures of the next day to be higher. The temperatures are much more stable if we have temperatures between 10 and say what it is 25. And then again, if we go above 25, the expectation is to go lower. This is a simple observation, and yeah, we can use this to some extent, making this kind of analysis. I mean, obviously, we're having different conditional distributions, and this can be very kind of feature dependent. This example can be extended, and I'm going to show how happened. I guess I'm missing a slide here. But this is terrible. Well, I'm sorry, I wasn't able to show it on this one. But let me take again. I'm taking a signal here, like say for the last 5 years in Atlanta's temperatures, and I'm fitting 5 quantiles, and I'm having this plot here. So what I want to do is to actually make a sequence of states. I can, at each point here, I know I can calculate where the temperature has been between the first and the second quantile, between the second and the third and fourth, and so forth. So I can make a sequence. Yeah, I see it, but there is also a break after that. So I think I'll extend to the end of 2:30. And so after that, I can basically, using the quantiles, I have made this sequence. These labels here, they show me in what states I have produced from this data. And this mosaic plot can give you some idea of how, what is the probability to move between this 6, I'm sorry, you cannot see this, but basically it gives you the conditional probability of where is this, what is the probability to switch from one temperature interval to another temperature interval. This was explained in the other slide, and as I said, I'm missing a slide here. I wanted to compare what happens if I do this kind of sequence partitionings using quantile grid and uniform grid. And I was saying that I have this kind of labeling function which separates the temperatures in intervals, and then using these mosaic plots, I can actually have a visual representation of the conditional probabilities. I mean, you can see if it is 11, it kind of stays, it's most likely to stay at this 11. So if it is in this 11th kind of range, it's most likely to stay at the 11th range. Like I see here on my yellow squared yellow rectangle, where the probability is 73%. When we are at 12, I can see that the probability to stay at 12 is in the range number 12 is this one. Sorry, this one. The probabilities to stay there is 49%. and it's 45% to go at 11. So this is kind of more or less similar to what we observed with the distributions, the grid plot of distributions. So I'm further, this actually, we can apply other sequence mining algorithms, like I can use tries, the so-called tries, which give me the probabilities of the conditional probabilities. And what is happening is, I mean, this is more or less rephrasing in this particular case what we see in the in the mosaic plots. But knowing the probability of one of the states, I know what is the probability of another state to occur after this state. Very simple, you know, my sequence mining was done by doing partitioning of the states in this way. All right, so basically, this is the main functionality implemented. Away some, this finding of the nonlinear data is more or less, it's interesting, but you can find it in community. The future plans is to actually write a naive Bayesian classifier which uses quantile regression. In applications like, say, R or SAS, naive Bayesian classifiers, they use the assumption that when we have continuous variables, for certain classes, we will get normal distributions. There is no need to have this assumption. With quantile regression, we can actually extract the real signal at that point. A very interesting perspective, very interesting project is to do multidimensional quantile regression. And I'm going to show, this is a work in progress, so you can see, like if I have some cloud of points, I can fit different regression quantiles here. This is not exactly that trivial. We can see how this curve here has been kind of twisted. There is lots of computational geometry considerations to be done. I mean, I'm currently working on that. So to give you an idea how this is done, I'm basically taking this cloud and I'm rotating it. I'm rotating it on different angles. And at each angle, I have found this point, which is a regression quantile around 0.95. And then I find the envelope of the corresponding curves. And then to find the envelope, I need to find the intersection points. So basically, this is it. And thank you for your attention. You can find more information in these links.